Hi all. In this presentation, we will go over the replication of Sloan 1996, which is the accruals anomaly. The accruals anomaly is the phenomenon that firms' accounting accruals have a negative relationship with the subsequent stock returns. Accrual stands for the expenses of a firm in a certain period that would not be paid until a future period. For example, two firms could report the same earnings in a quarter, but one with the higher accruals would actually have a lower cash flow. However, because of the inefficiency of the market, investors could not process information about how accruals immediately, resulting in firms' higher accruals to yield lower future returns, hence the accruals anomaly. Computationally, accruals have three components: current assets minus current liabilities, and depreciation expense. In terms of Compustat items, current asset equals change in current asset minus change in cash. Current liability equals change in current liabilities minus change in debt included in current liabilities, and change in income taxes payable. And depreciation expenses is directly included in Compustat. Finally, the three financial variables are calculated as follows. Earnings component equals income from continuing operations divided by average total assets. Accruals component equals the previously calculated accruals divided by average total assets. And cash flow component equals earnings component minus the accruals component. Okay, so now we're going to go over the results of our replication. So in table 1, we rank firms into 10 deciles based on their accruals component and print out the summary statistics of each portfolio. And so you can see that here. These are the 10 deciles. Table 1 presents summary statistics, mean and median values, different characteristics of 10 deciles of firms ranked based on accruals. Panel A presents the three financial components of earnings. Panel B presents the alpha and beta from a CAPM time series regression of each portfolio and the size of firms. And panel C represents the three subcomponents of accruals. So you can see panel A, component of earnings. Panel B, risk proxies. Panel C, subcomponents of accruals. Okay. Now, with respect to table 2 through table 7, we run different regressions to test for the accruals anomaly. All of our results show a similar trend. Although the accruals anomaly is still somewhat apparent, it is significantly weaker than the observation of Sloan 1996. We will go more in depth about the formulas of these regressions in the Python code. Now we will go into step-by-step through the Python code that we use to get these results. First, we connect Google Drive and import tools. Next, we import the CRSP data, which is what you can see here. And the CRSP data is basically the return data. And we do it for 1990 to 2022. Next, we clean the CRSP data and filter it with the following criteria. Data which is from after 2018, from the New York Stock Exchange, American Stock Exchange, and the NASDAQ, US-based common stocks, and no infinite or missing values. Also, a new function introduced in this code is the pandas merge function. In the section add deciles of market values. This is the same as SQL left join. In simple situations like this one, using the pandas merge function reduces runtime because it avoids the conversion into and from SQL. Next, we import the Compustat data. Here we are importing the Compustat data. Compustat data is basically the fundamental data, and we imported the annual fundamental data from 1950 to 2022. Finally, we also clean the Compustat data, filtering for INDL industry format STD data format and dates after 2017. We calculate the change in each relevant item with the function and calculate accruals with the previous equation. We also standardize all components by the firm size, average total assets. Again, we use the merge function to maximize the efficiency of the left joined. Next, we merge the two data frames, CRSP and Compustat, together to generate our new main data frame. Then we import the Fama-French results to get the relevant risk-free rates and the risk-free premiums. And you can see that here. Again, we're importing Fama-French data to get the relevant risk-free rates and risk-free premiums. We again clean the data. Since Fama-French data is in percentages, we divide by 100 to get the percentage values. We then calculate the annual risk-free premium using the product function. We merge the Fama-French data into the main data frame, calculate the abnormal return of every row by subtracting the expected return based on average of size decile from the adjusted return. Now that we have prepared all the data needed, we can begin replicating tables from Sloan 1996. For Table 1, Panel A, we simply print out the summary statistics for each accruals component decile. To do so, we loop through integers 1 to 10 and filter for only that decile every time and print out the 3 financial variables. For Table 1, Panel B, we first calculate the natural log of the market value to get the size and print out the mean and medium sizes for each portfolio. We also calculate the annual return minus risk-free rates to prepare to run the regressions. In the next step, we run regressions based on the CAPM model, which is the annual return minus risk-free rate on the annual risk-free premium, to calculate the alphas and betas of each portfolio. Here, the intercept is the alpha, while the coefficient for the risk-free rate is the beta. Finally, we print out the summary statistics of the 3 sub-components of accruals for Table 1, Panel C. You can see that here. Okay, and then this is the properly formatted complete Table 1. You'll notice there's a descriptive paragraph up here describing what's going on in the tables. We've got the equations, which describes what we were doing. And then we have Panel A, Panel B, and Panel C. Next, we run 2 regressions for Table 2. The first one is future earnings on current earnings, while the second one uses decile values to eliminate bias. We get the future earnings data by shifting the data by -1. This is the properly formatted regression results for Table 2. And again, you can see we have a descriptive paragraph up top. We've got the equations, we've got the pooled regression, and we've got the industry level mean Q1, median Q3 regressions. And then same for Panel 3, except using decile rankings. In Table 3, we run similar regressions, but this time on the 2 components of earnings, accruals and cash flows, and their deciles. This is the regression results for Table 3. And again, we've got the descriptive paragraph, we've got the equations, we've got the pooled regression, we have the industry level regression, and then we have the regression using decile rankings, again, pooled and industry level. Now we prepared the data for Table 4 regressions, which required some more data preparation, which simply compounds abnormal return data 4 months after the end of a fiscal year. We take the component returns after 1 year and 2 years for our next tables. After preparing the data, we run 2 regressions for Table 4, Panel A. We first use the simple regression of future earnings on current earnings again. We store the alpha 0 value or intercept of that regression with the parameters function, which stores the array of all coefficients of regression. We then subtract the alpha 0 from the earnings component. Then we run the second regression of future abnormal returns on future earnings and current earnings minus alpha 0. In this regression, -1 at the end tells Python that the intercept is 0. since the intercept is already included when we subtracted a constant from current earnings. In our regression results, beta is the first coefficient, and alpha 1 is calculated by dividing the second coefficient by the first. See Sloan 1996 for more details on the regressions. In panel B, we use the exact same process with decile values instead. And finally, here are the regressions results for table 4. And again, you'll notice the format with the descriptive paragraph, the equations, panel A and panel B. Table 5 uses the exact same data set and similar regressions as table 4. Instead of using current earnings, we use the two components, accruals and cash flows, to run the regressions. In panel B, we again run the same regressions on variables decile values. These are the results of our table 5 regressions. In table 6, we recalculate the risk-free premiums and return minus risk-free rates, this time at 1 year and 2 year periods, starting at 4 months after fiscal year end. We run the CAPM regression again to get Jensen's alpha and print out the abnormal returns and the alphas for table 6. Here are the results of table 6. We've got the size adjusted returns for year t plus 1, year t plus 2, Jensen's alpha for year t plus 1 and year t plus 2. And if you aren't familiar with Jensen's alpha, please look up our Jensen's alpha video. But it's really just the intercept from the model. Finally, we run regressions of 1 year and 2 year compound abnormal returns on accruals and the 3 subcomponents of accruals to evaluate the extent to which accruals affect future stock returns. And you can see that here in table 7. Table 7 shows the regression coefficients for 2 different regressions. Panel A runs the regression with only the accruals being the independent variable to investigate how much the returns depend on firm's accruals. Panel B runs the regression on the 3 subcomponents of accruals, investigating which components play the biggest role in the firm's future stock returns. Anyway, so I hope you found this video helpful. This is basically the how to code up Sloan 1996, the Accruals Anomaly, and I will see you in the next video.